This is when you start to see what calculus is used for. Up until, because nobody's really going to walk up to you on the street. I doubt they would ever walk up to you on the street and ask you to do math, but nobody's going to walk up to you and say, what's the derivative of this, right? That's like, it's kind of just artificial to do that. But calculus is applied in physics, engineering, chemistry, all these different places. And this is the beginning you start to see where it's applied. So, all right, let's just do an example. We are draining the water. If I say conical tank, do you know what I mean by that? It's a cone, basically, all right? So we have a cone. That's a pretty good cone for handwritten, I would say. Nothing? Nothing.
It's okay.
I'm looking for validation here, people. There's your radius, and there's your height. All right. We're draining the water. We're filled it with water. We're draining it out. Okay. Does anybody know what the volume of a cone is? The formula.
Wasn't it like 4/3?
Oh, you're close.
1/3?
He's just looking it up right now. So
the 1/3 times pi.
It's pi over 3 or 1/3 if you want to do that. R squared h. That is the volume of a cone. And so this is where calculus becomes powerful, because up until this point, you've just said if the height and the radius are certain numbers, what's the volume of the cone? Or if I know the volume and I know the height, I can figure out the radius. It's all just static, all right? But I think he said it, and I think I might have said it. Calculus is the math of change. Like how are things changing? Okay? So we're doing rate problems. A rate problem is with respect to time. So you're deriving everything with respect to time. Okay? This bit right here. So when you're doing the derivative, this is why we have to do implicit. The bottom of the derivative is dt. All right? There are no t's in here. So we have to use implicit differentiation on this expression. So if I want to know how the volume, the radius, and the height are all changing with respect to time, I derive it. So I go, okay, the derivative of v with respect to time. Now you can't write, now this is, for me, I'm a stickler for this, and I don't know if he will be. Up until this point, when you were doing implicit, you were, well, the question we just did. Where is it? We just wrote y primed, right? Because it was dy dx is what you're actually doing there. You're going dy dx, but I'm just going to call that y prime. Problem is, you shouldn't do that when you're doing implicit, because you're going to have r primes, h primes, and all this type of stuff. So what I would want you to do is I would want you to say the derivative of v with respect to time is just dv over dt. Change in volume with respect to time equals. And now we have to do this stuff. Pi over 3 is a constant. So what can you do with constants? Just pull them out, right? Like you don't have to worry about it. So I'm just going to write pi over 3 here. Now, I need to derive r squared h with respect to time. What rule do I need to use on that? Product rule, right? Because it's two variables being multiplied by each other. So we go, okay, what is the derivative of r squared with respect to time? You know, drop the 2 down. So you'll get 2r. That's the I could write to the power of 1, but I'm not going to because I'll confuse it with primes. So it's 2r times the derivative of r. What's the derivative of r with respect to time? Not r primed. dr over dt. It is r primed, but ask him what he expects, okay?
So like instead of writing like R prime, it would be
dr dt. They're I don't want to say they're the same thing because when you just write y prime, you don't know what you're deriving with respect to. But when you write it this way, you know exactly what you're deriving with respect to, right? So dr dt times the first function, which was h. Now that's the derivative of r squared. Now I have to do product rule says I have to add that to the derivative of h. What's the derivative of h? dh over dt. It's not 1 or times r squared. It's not 1 because this variable and this variable don't match, right? If they match, then you can just do your regular derivative. But because they don't match. Now, I just wanted to show you, that's the expression. We're not solving anything yet. Okay? So you can see you have three things that are changing. The volume is changing with respect to time, the radius is changing with respect to time, and the height is changing with respect to time. And you can see that if you look at a picture of a cone, as the water level goes down, the height is changing, the radius is changing because the cone is getting thinner, and the volume of water in it is changing as well. So three things are changing now. So we took a static equation that just relates three variables. If you have this and this, then I know what this is. To a rate equation that now relates all the different rates of how things are changing as it's moving up and down. Yeah.
If it wasn't connected to time, would we not have to find like add the derivative? Like in respect to t?
It would be how you wanted to, like you could say how is everything changing with respect to the height or something like that. So it'd be over dh, say. You could do that, then it's not a rate problem.
I'm just saying, like, if you had like another variable in an equation,
Yeah.
And it just wasn't connected to t, or like it doesn't change the time,
then it's constant.
then it's a constant.
Yeah, you will. I think we see one of those. So if it's constant, you just make it a constant. You know the derivative will be 0, so you can essentially just pull it out. Okay.
Isn't it always going to be dt over dt?
It's always going to be over dt because a rate problem is, by definition, with respect to time, right? Okay. Let's go to 3. That's second question is kind of weird. We drop a pebble into a pond, causing ripples to spread out. The radius of the outer is increasing at a constant rate of 1 foot per second. I stole this from an American book. That's why we're in feet per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay. It's a circle, right? You drop a pebble into a circle, into a pond, you get a circle, correct? Okay. I want to know how the area is changing. So what's the area of a circle? So the first thing you need to do is you need to have a formula. What is actually changing? Now, I want to know how everything's changing with respect to time because it's a rate problem. So what do?
Derivative.
Take the derivative with respect to time. So what's the derivative of A with respect to time? dA dt equals. What's pi? It's a constant. So do I care about it? No, I pull it out, right? Because I don't want to deal with that. R. Now, R is changing, right? Because the radius is getting bigger of the circle. So I need to take the derivative of R squared. What do I do? What rule am I using? Chain rule or power rule or whatever you want to call it. So 2 falls down. 2 times R times the derivative of R, which is dr dt. Okay, now we can actually solve this one. So we got to go back to the question and look at what information they've given us. They've said the radius of the outside is increasing at a rate of 1 foot per second. What does the 1 foot per second represent? Sorry? The rate of what?
The radius changing.
Oh, the radius change. Sorry, it's hard to tell when.
No, he was talking for.
Oh. So this is dr dt, right? It's how the radius is changing per unit of time. And it's changing at 1 foot per second. That's why it's over t. So that's my dr dt. They tell us the radius is 4 feet, so that's clearly just r is equal to 4. And then they say, what is the total, at what rate is the total area changing? So what is that? What are they asking for in the equation? It's the only thing that's left. dA over dt. The change in the area with respect to time. So I just plug everything into my formula. The radius is 4 feet. dr dt is 1 foot per second. 1 foot per second. And just to show you that the units will work out as well, if you have pi in your equation, because pi is irrational, goes on forever, don't actually use it. Just write pi. So for example, I'm going to go 2 times 4 is 8, times 1 is 8. So I'm going to write 8 pi feet per second. Now you can use 3.14, but you're rounding off, so it won't be as accurate. But you can still do it, but I'll think less of you. I know. It's like mixed fractions. So you just say 8 pi feet. Actually, it's feet squared because it's feet times feet squared per second. And that makes sense because we're asking how does the area change? And area is always units squared. Okay? And the units work out. It's area per second. All right, next one. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches, again, US, per minute. Find the rate of change of the radius when r is equal to 2 inches. Okay, what's the volume of a sphere? Or r cubed. 4/3 pi r cubed. I do not expect you to memorize these. All right? I would give them to you or give you a sheet with all the formulas on them. The volume, I have no idea. Okay. What do I do? What do you do every time for a rate problem? Derivative. Yeah. Once you have your formula, derive it with respect to time. Go. We'll see if we get the same. Just like in our measurement. You ready? 4 pi r squared dr dt. People agree with that? 3's cancel, right? Because 4/3 pi I can just pull out, derive r cubed, which is just 3r squared times dr dt. And then the 3's will cancel. I mean, you don't have to cancel the 3's, but. Is that okay? All right. Now we just got to plug everything in, figure out what we're solving. Well, what are we solving for? Rate of change of the radius. So what am I solving for in here? dr dt, right? That's what I want to know. I want to know this is dr dt. I want to know what that is.
So can't we just divide off the 4 pi?
You can divide all this off if you want. Or you can plug it in and then divide off. I don't really care. I know in physics, they tend to just do that all at the beginning, right? Solve for your unknown. I don't care what you do. I'm just going to plug everything in and then do it. So, what's my dv dt?
4.5.
Yeah. You know that is dV dt because it's cubed, right? Volume is always units cubed. And they tell us the radius is 2, so I'm just going to plug everything into the formula. 4.5 cubic inches per minute is equal to 4 pi, it's our 2 inches squared dr dt. All right, I'll let you solve that now. I think I put the pi in this time because it's in the denominator. Ready?
Yeah.
0.09 inches per minute. And the units work out again because you square the inches down here, and that's cubic inches. So you subtract the exponents, you're left with just inches to the power of 1. Excuse me. Yes.
Like, can I leave the pi in the denominator?
You can.
Okay.
So if you wrote, I don't know, what is it?
It's 0.28 multiplied with the pi.
Oh, that's ugly. It's still right, yes. I know. But a decimal with the pi? Now you're just...
Like, here's 0.3 over pi.
Why is my answer different?
We're rounding. We're being around the bottom.
Squaring the 2, 4.4 times 460.
Oh, you're correct.
You go divide by 4.
Yeah, so it's 4.5 by 16. Is that the bottom? You can check
Okay, is everybody good with that? All right, I got a thumbs up, so I'll take it. All right, last question. I'll give you a couple practice, and then we'll move on to the trickier ones. All edges of a cube are expanding at a rate of 3 centimeters per second. How fast is the volume changing when each edge is 10 centimeters? So we got a cube. I'm just going to use S for all the sides, even though it doesn't look like a cube, because it looks more like an elongated rectangle. But what's the formula for volume of a cube? Yeah, but they're all the same, so it's S cubed, not S squared. All right. Go. Do it.
Like, finish the entire thing.
Finish the entire thing. What's the first step?
Derivative. No.
Derivative. It's always the derivative. If you don't know what to do, take the derivative. I'm doing galaxy. 900?
Yeah. Are you taking marks for not having units?
No. No. If it was physics, I'd care, but yeah. I'm not going to be a stickler for units. I'm going to be more of a stickler for the math.
What about JM? Do you know his policy or we ask him?
You're going to have to ask him, and he's a physics guy, so
Yeah.
he might. I'll take 0. Okay. All right. The last little bit here before I give you a couple practice questions, and then we'll move on to the trickier stuff. So it's basically just kind of getting used to what the words will mean. Like in these ones up here, it's kind of straightforward. I tell you the edges of a cube are expanding, but it's the units that kind of key you into what that number represents. Because it's 3 centimeters per second, I know that's how each side is changing. Up here, it was 4.5 cubic inches. Because it's cubic, I know it's volume that's changing. So if I say the velocity of a car is traveling at 1 hour and 50, has been traveling at 50 miles per hour, that means that, and x is the distance traveled, the derivative of x with respect to time is 50 miles per hour. dx dt is equal to that. It's the velocity. That's the velocity thing. You take the derivative, you get the velocity function. Take the derivative of that, you get the acceleration. If I say we are pumping water into a swimming pool at 10 cubic meters per hour, then what does that 10 cubic meters per hour represent?
Volume.
It's the change in volume, right? So it's dv dt. So most of it's straightforward. When you do angles, which we're going to see in a bit, there's a slight trick to it, okay? Because you need to be using rads, all right? So, remember from Math 12 that 1 time around a circle is 2 pi rads, right? So if I say there's 25 revolutions a minute, how fast is your angle changing? What's d theta dt? 2 times that. It's 50 rads per minute. Okay? We're going to see the angle stuff in the next few. All right? So I'm just going to give you like 10 minutes to do a couple of questions. Sorry.
Is it 50 pi or 50 rads?
Oh, 50 pi. Thank you.
Oh, okay.
Thank you very, very much. That is actually a big one. Because you're multiplying it by 2 pi. 50 pi rads. So it's actually 150 something rads if you actually multiply the pi. So, sorry, thank you for that clarification. All right. Okay, here's a couple practice questions. Page 152, 1, 3, not 5, 11, 13, 15, and 17. And I actually have a feeling I don't want you to do 1, 3, 7. Let me check.
There's a phone in there.
152. I actually just want you to do.
This one's so fun. Okay. See, you guys are right. A crumpled up piece of paper.
Yeah, let's just do 11. Forget those ones. 11, 13, 15, and 17. You're not going to get them all done because I'm only giving you 10 minutes. I want to just start so that you see the next level of stuff before tomorrow.
Is it 153?
I don't know, is it?
Well, there's no questions
Yeah.
for 152, so.
It is 153.
Jeez. All right, part 2. So the part 1 is basically it's some known formula. It's usually some geometric shape, circle, sphere, cone, whatever. But there's a known formula. Okay. Part 2 is you don't get a formula. You have to generate the formula. Okay. So this is another little level to it. These are the more the physics type problems. So we have an airplane flying over a radar tracking station. It's all labeled. This is our S. This is the height. S This distance here is changing at a rate of 400 miles per hour. What is the speed of the plane when s is equal to 10 miles?
Do we have to convert kilometers to miles?
No, we'll just do it all in miles. I don't care. We can change it to kilometers.
The plane is 6 kilometers. Yeah, the plane
Oh!
is quite low.
Oh, let's make it all kilometers. Sorry.
Okay.
Sorry, that's my fault. Sorry, make them all kilometers. There we go.
It's frozen.
Is that better?
It's frozen.
Oh my gosh. There we go. Change everything to
Wow.
kilometers.
That was instant. Wow. You're so fast.
I know. And you didn't even see me right.
Yeah, that's crazy. It's just the
Magic.
spider abilities.
Sorry, I should have been consistent with my units. We're not in unit conversions here. So, okay. So we're 400 kilometers per hour because it's speed. There we go. What is the speed of the plane when s is equal to 10? Okay. Now, there's two types of problems you will get in part 2. So essentially 3 overall. There's the ones where you get a formula. That's part 1. Part 2 is when you have to generate the formula. And there's 2 types that you will see in Math 100 for the most part. The first part is a Pythagorean problem. We have a triangle. It's a right angle triangle. I've said nothing about angles, so it's not a trig problem. Okay? If it's not a trig problem, it's a Pythagorean problem. The other type is a trig problem, and that's what we'll do down here, but it's always going to be right angle in this class. For Calculus 12, I would say for Math 100, but I can't speak for him.
Okay.
But I've never seen a non-right angle problem in Math 100. Okay? All right, so the first thing we have to do is put some variables here. So I'm just going to call, just to make it easy, that's x, that's y, and we'll just leave that s as s. They've already labeled it as s. Okay, we're not doing trig, so if we're not doing trig, we have to be doing Pythagorean. What's the Pythagorean formula?
X squared plus y squared.
X squared
No.
plus y squared is equal to
Where are you getting A? What if I wrote it as A and B?
s squared. Okay, now, is anything in this problem a constant that does not change? 6 kilometers. The height of the plane is not changing. I haven't said anything about the height of the plane changing. Okay? Put that in right away. Okay? Because what happens when you do the derivative of a constant? It goes away. So it'll make our life easier. Okay? So I put 6 in. You could write 36. I don't care. Doesn't matter. All right. So now this is our formula. Okay. X squared plus 6 squared is equal to s squared. So they're asking, what is the speed of the plane when s is equal to 10? So what is going to represent speed? Okay. It's going to be something over dt. What over dt?
DS.
Not ds.
DV.
dx. If you're in a plane flying, your speed is always relative to the ground, right? So it's dx over dt. That's what I want to know. All right, so what do I do? Once you have your formula, if you don't know what to do, what should you do? Take the derivative with respect to time, right? These are rate problems. So derivative of x squared with respect to time is 2x times dx dt. The derivative of 6 squared is 0 because it's a constant. So that made our life easier. Equals the derivative of s squared. Two s times ds dt. All right. What are we trying to figure out? Dx dt. So what should I do with the 2x? Divide it off. What happens to the 2's? They go away. Okay. So now I've got my formula. I just got to figure out what S, X, and ds dt are. What is S? 10. They tell you in the question. $10. What is ds dt? That's 400. That's this, right? Because it's how S, they tell you S is decreasing at a rate of blah, 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 blah. So that's 400. Do I know X? I do not. How do I find X? You put it into that formula, right? Because the 6 is constant, and they tell us what is all this happening when S is equal to 10. So if that's constant, they tell us this is 10, I can use the formula to figure out X. So is equal to 100 minus 36. So X is equal to 8. It's actually plus or minus 8, but we ignore the negative 8, right? Because it makes no sense. Yes? So X is equal to 8. Now I just plug it into the formula. 8 what? Kilometers. Right? So you plug all that in your formula and you end up with, I think, 500. And because those kilometers cancel, you're left with kilometers per hour. Is that okay? Just one extra little wrinkle in that you have to generate this, realize that this is constant. If you don't put that in as a constant and you just derive this, you're going to get a bigger equation. Okay? We will look at equations later on where that is changing. It's not a constant, but it's going to be a bigger equation. You'll have 3 variables. All right. And then you will have to use this equation to find another variable later on, somewhere in the problem. And then just plug it all in and you're done. Are we okay? All right. Now the angle one. So find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. So we got a rocket ship flying into the air. Its height is described as 50 times t squared. It is 2,000 meters from the camera.
What does it mean by 2t squared?
Time squared. T is time, sorry. Yeah. Okay. All right. So they want to know the rate of change of the angle of elevation. So if this is theta, what they're asking for is how theta is changing with respect to time. D theta dt. How fast is the angle moving up of the camera? All right. This is a trig problem because we have angles involved. It's not Pythagorean theorem. It's a right angle trig problem. There's my angle. I have this piece of information, and I have that piece of information. So what trig function am I using? Sorry? TOA. Tan, right? Opposite over adjacent. So you write tan. Just write it out. Tan theta is equal to the opposite side, which is h, over 2,000. The 2,000 isn't changing, right? The camera's not moving. The distance, the rocket's just flying straight in the air. We're assuming straight up. Might be a bit of a non-realistic thing, but I don't know. We're going to pretend that it just goes straight up. For a short period of time anyway. Like 3 seconds after liftoff. even though they're saying 10 seconds after liftoff. We're going to extend that. Okay. All right, tan theta is equal to h over 2,000. What do I do once you have a formula? Derive it. We're in the derivatives unit, right? We're deriving with respect to time. This is where things get a little wonky if you're not careful, okay? What's the derivative of tan theta with respect to time? What's the derivative of tan? Secant squared theta. But we have to use chain rule. So now I have to do the inside derivative because theta is not constant. What's the derivative of theta with respect to time? D theta over dt. Equals. I'm going to pull the 1 over 2,000 out just because that's a little easier. What's the derivative of h with respect to time? dh dt. All right. What am I solving for? D theta dt. So what do I need to move? Secant squared. So I can divide that off. But if you remember, what is secant? What is secant? It's 1 over cos, right? So if you think about it, I could write it like this. You don't have to write this. I'm just going to show you. How do I get cos squared to the other side? You just multiply it up. So you can get d theta dt is equal to cos squared theta over 2,000 times dh dt. That is my formula I want to use. Okay. So what do we do now? What other piece of information do I have? I do? No, that's t, right? This is time. Time isn't even in our formula. I mean, I guess it is dt, but do I know theta?
No.
No. Do I know the height?
Yeah.
I can figure out the height, right? But are they asking for the height?
No.
What is required for this formula? dh over dt is required, right?
Yep.
Can I find dh dt?
50 times. Yeah, 50 times.
It's not 50 times t. It's dh dt. So if h is equal to 50 t squared. I take the derivative of that to get dh dt. Now, does this match this unit?
Yes, it does.
So you can just do a regular derivative, right? So what is the derivative of 50t squared with respect to time? 100t. So we can either put our time into this now, or we could plug that into there. It doesn't actually matter. Since we're here, we might as well do it right now. Does that make sense to everybody? So I know that my time is 10 seconds. So dh dt is 1,000, right? And it's how fast the height is increasing. So it's 1,000 meters per second. I should have put units on that, but I didn't. So dh dt is 1,000. Okay, we've got that. What other piece of information do I need? Well, I need to know what theta is, right? Okay. What can I use?
Inverse tan. R tan.
Yes. So I'm going to use our original. You just wanted to say that, didn't you?
I know.
And now, if I know the height at a certain time, I can figure out theta. Does everybody agree with that? Okay. Can I figure out the height? Yes, because it's 10 seconds after liftoff, and our height is defined as 50 times t squared. So h is equal to 50 times 10 squared, which is 5,000. So our height is 5,000. So now I can put that into there. I have tan theta h, which is 5,000 over 2,000, which is really just 5 over 2. Reduce it. And then define the angle. 10 to the minus 1 of 5 over 2. It doesn't matter if you're in rads or not, because we're punching it into another trig function, okay? I'm going to do it in rads just to be consistent. If theta was by itself, it wasn't in anything, then rads is important, okay? Because you can't just insert like degrees as a unit if it doesn't make any sense. But if you're putting it into another trig function, it doesn't matter if you enter pi over 4 rads or 45 degrees, it's the same thing. So the inverse of that gives me 1.19 rads. I'm going to do mine in rads. So that's my theta. Now we just slam everything into the formula. d theta dt is equal to cos 1.9 rads. It's all squared over 2,000 times 1,000 meters per second. And this 2,000 is in meters. All right. So what do we get? 0.069. What are my units? Rads. So the meters will cancel, but the seconds don't cancel. So it's rads per second, which makes sense, right? That's how the angle is changing. All right. I want to give you a bit of time. There's only 10 minutes left of class. I don't want to do the next two examples, which are just variations of this. Okay. I'll do them and put them in a video later on, so you can do them as practice. Questions from the book that you should do. 152, numbers 21A, B, 25A, and 39. That was very quick. Usually I split this up over a couple